Dr. Vivek Saxena founded AdvisoryAero OSC after 30 years in academics, aerospace industry, and consulting, where the company mainly targets the massive unmet need for digital technologies in operations and supply chain functions in the aerospace industry. Previously, he held a variety of roles as a chief engineer, plant manager, president, and CEO at various aerospace companies. He has a PhD in applied math from the University of Cambridge. His work at Cambridge and Cornell focused on modeling of complex phenomena like gas turbine combustion and stochastic simulation techniques. Finally, Dr. Saxena has a personal connection to the University of Minnesota and the Twin Cities. So as an MS student at the university, he contributed to the design of St. Anthony Falls Wind Tunnel. So with that, let's welcome Dr. Vivek Saxena. He's going to talk to us today about digital technologies in aerospace manufacturing, a perspective from the industry. So
thank you, Krishna. Appreciate it. I'd like to thank you and the department for inviting me for this seminar. I've been enjoying discussing various topics with various faculty members all day, and it's been a very worthwhile experience. So I hope I can return the favor during this presentation and leave you with something interesting, some new knowledge, perhaps some things to ponder. So I realized, since I used to be on campus, you're not too far from Ackerman Hall. So, but I don't know how often you talk to aerospace folks. So I thought I'll start by briefly talking about aerospace manufacturing and supply chain, just to put it in perspective. If you're not used to, the kind of peculiar or unique aspects to aerospace manufacturing and how the supply chain is structured. Then we'll talk a little bit about the challenges in aerospace manufacturing that make them particularly amenable to digital technologies. And then we'll go briefly over some of our recent experience in applying digital technologies in aerospace manufacturing, and some examples where we have done simulations and optimizations and some other methods to see how effective they have been, and also, what is in the future for those methods. So a lot of this is, the examples we're going to be giving to you are from our engagements with clients. And to give you a sense, we have worked with small companies as well as large companies, but most of the examples I'm going to give you are going to be for what I call small and medium-sized companies, so typically less than $500 million in revenue. So, and by the way, feel free to interrupt and ask questions if you think that you have anything to discuss. We have an hour, and I had prepared to finish this in about 45 minutes and give 15 minutes for Q&A, but it could be interspersed with the presentation. So please feel free to ask questions whenever you have any. So aviation market, just to get a sense of the structure of that, if you're not from aviation markets, we look at it as 4 major market segments. So the columns are the 4 major market segments. They are air transport. So this is the jetliner business, right? The Boeing and Airbus planes that are flown by airlines. Then you have military, you have civil helicopters, and then you have business aviation. The military helicopters are included in the military segment. So that's how we view the entire aviation market. So you've got 4 segments. And there are 5 major ways to make money in this industry. You can either build things, you can build a whole aircraft, you can build a system, you can build a component, right? Or you could finance. So there are lessors, there are banks, there are investment agencies that finance the purchase of those aircrafts or operations of those aircrafts. You could make money by operating those aircraft. So that would be the airlines. For air transport business, for military is the countries. For civil aircraft, it could be petroleum, oil and gas industry, could be, and we have given some examples there of some of those players. You could also make money by fixing those aircraft. So that's aftermarket MRO world. So here are some of the lists over there of people who work in the fixing world. And then you can provide services. So in services, everything from cleaning the aircraft, providing fuel services, doing catering. But it's a huge market. Overall, it's estimated that aviation market is, over $500 billion market, $500 billion with a T. And if you look at individual pieces, the service market alone, if you look at LSG Sky Chefs, when you go on a plane and people who give the catering business alone globally is 15 billion with a B size markets. It's fairly large. So I think that this gives you an overall picture of how we look at the structure of the aviation industry and what the various revenue streams are. And then let's look at the supply chain. So the supply chain is essentially tiered. You start with the OEMs on top. So you have Airbus and Boeing making aircrafts. And then engine guys are also seen as OEMs because when airlines buy a plane, they also buy engines directly from the engine OEMs that are offered on that plane. So you have OEMs on top, original equipment manufacturers. Then you have tier ones, people who are supplying systems, provided sub-assemblies and components at the next level, which is tier two. And those are some players. And there's some confusion about where a company resides. It could be both tier one and tier two. It could be tier one, tier two, and tier three in some cases. So it depends on who they are supplying and what kind of assembly components or sub-assembly they're providing. Then you have tier three, which is component level manufacturers. And these could be really small machine shops. You have quite a few of them in Minnesota also. If you know the old Remley plant, which got divided between aerospace and medical devices. And there's an aerospace plant here that actually is part of ATI, which is a much larger tier four manufacturer. And then you have at tier four, raw materials. So these are guys who provide material or forged material, or cast material, which is then converted into components, which is then converted into sub-assemblies and then assemblies and all the way to the aircraft. So that's the tiered structure. And the point we're making here is that a whole bunch of tier two, threes, and four, and not four so much, but twos and threes, are thousands of small machine shops, manufacturers, making microelectronics, making components that go into landing gear, making plastic parts that go into the cabin interior. And they're all important for the assembly of the aircraft, but they are too small to actually benefit from some of the technology advances which are taking place. So if you talk to a tier one, so we know in Minnesota, we have Collins Aerospace, for example. I bet if you talk to somebody at Collins, they'll tell you that 90% of their suppliers are late on delivery, if not more. And so it's a very inefficient supply chain. And I attribute at least part of that from my personal experience of 30 years in this industry is that a lot of small players, a lot of tier two and tier three suppliers have not benefited from all the advances in operations research that department like yours produces into something which is practical for them to use. So there are multiple reasons for why they're not using it, but that's the reality. So our mission as a consulting firm is to actually target that market of companies which are less than $500 million in size, that are not going to go and invest millions of dollars in technology, don't have a lot of engineering and IT talent internally to develop their own solutions. They would want a third party like a consulting firm like ours, AdvisoryAero, to come and help them. So that's what we do in terms of as a firm. Any questions on supply chain? That's fairly straightforward. So let's move to.
So I have one small question. So you mentioned that like there are these four sectors or classes where like the military, business, aviation, and transport. So is it I mean, is it the case that in all of these there isn't that much of a like penetration of modern sort of optimization tools, or is it specific to certain classes, or like? So I would say at least like in business aviation, perhaps there is a more of an incentive to like become more efficient.
So business aviation economics is very different
Mm-hmm.
from, actually same thing with civil rotorcraft.
Mm-hmm.
It's economics very different, but I would say that if you look at a typical component supplier in any of these segments, first of all, many of them actually supply to all those segments. So I would be working with a machine shop and they're supplying to Gulfstream as they are supplying to Boeing. So that issue about technology, lack of technology penetration is across the board. However, you're right that there are certain technologies that have found faster adoption in business aviation segment. So for example, if you think about something like composite material adoption. So everyone knows composite is, lighter, so it's a good thing. It also gives great finish. And when composite was not very mature as a technology for larger aircrafts, or Boeing and Airbus were very reluctant to incorporate, business aviation actually jumped in and they got a lot of the composite parts very early on. So yes, there are certain places where they have been quick to adopt, but when it comes to enabling technologies for their manufacturing, which is what we are focusing on, operations related technologies, I think that goes across the board.
Okay, thank you.
Yep, good question. So then just one slide on the side of the market. So if you look at that build part of the market across the board, it's about little less than $200 billion. In 2019, it was a $177 billion. 2018 was actually more, and that's simply because in 2019, 737 MAX was grounded, which is a big piece of the market, right? Because that's a very high volume aircraft. And then it gives you the breakdown by narrow body, wide body. And so it's a $177 billion market in just build side. And as I mentioned to you before, all the 5 revenue stream combined is over $500 billion. And some people say close to maybe even 800 billion market. So that just tells you the size of the market and where we are situated in the supply chain. Some of you may be curious about, well, so what is happening to manufacturing side of the business in COVID as an impact from COVID? So we have done some projections. We have used data which assumes traffic recovery by the end of 2023. Although recently, a few weeks ago, I saw that IATA has projected that pre-COVID recovery to pre-COVID levels is going to be early 2024, so it's even later. But the net outcome is that there is a $300 billion impact to manufacturing business. So the dotted line was the pre-COVID projections of production values of aircraft. So these, by the way, are based on list values, which are usually highly inflated, right? So if Boeing says a 737 MAX sells for $75 million for whatever model, in reality, it goes for up to 40% discount. Okay, but these are based on list values. So based on list values, there's a $300 billion impact in the next 5 years to the production side of the market. And that's huge. This is bigger than anything which has hit aerospace industry before. And some of the other things I want to show is that on the commercial side, you can see the recovery occurring and getting to pre-COVID levels by, as I said, 2024, 25. But on the military side, it's actually going along fine with a minor blip. And the blip that happened in 2020 is not because of demand. It happened because of supply chain disruptions. Because a lot of suppliers are doing both commercial and military. And I know of many suppliers at tier 2, tier 3 that just went belly up or had to lay off people, or there was a hotspot so they couldn't manufacture for several weeks. And so that's why the production value is expected to be lower in 2020 for military, but it's going to grow. So the top graph is for commercial and the bottom graph is for military. So you can see commercial takes a big bump and then slowly start to come back, whereas military at the bottom is actually getting along pretty well. And finally, last chart on aerospace industry is you can, instead of dollars, you can look at material consumption also. So we have a aircraft material model where we can go system by system, whether it's landing gear or cabin or engine or wing, fuselage, empennage, and we can predict how much material is going to be consumed based on the delivery schedule. And so typically, right now it's about 1.5, 1.6 billion pounds of material consumed in making these aircrafts. Bulk of it is aluminum. And then you can see there's only 5% composite. Although the newer aircrafts like 787 and A350 are supposed to be almost 50% composite, but their volumes is nowhere near all the other aircraft which are out there. So this is just tells you how, if you are in a material business, you're also seeing that drop and then coming back 2, 3, 4 years later. And it basically says that commercial side of the business is overpowering the military side of the business. And as we saw before, commercial side of the business is roughly 3 times the size of military anyway. So that's the reason why commercial drop actually impacts everybody all the way to tier 4. Okay, so we are closing the intro section on aerospace manufacturing and supply chain. Any questions at this point? Okay, so we keep moving. What are the challenges? So why is technology so important? And by technology, I mean enabling technologies for operations. So asset values are large. If you are assembling a Boeing 737 MAX in Boeing Renton facility where it is done today, it could tie up to $30 million in cash flow for Boeing. And if you don't deliver it because a fastener is delayed, a $10 part is delayed, it could delay a $30 million cash release for months. So having an efficient supply chain is that much more important because the asset values are so high. So you can imagine right now, after the 737 MAX grounding after the 2 crashes, there are over 400 aircrafts that are parked, brand new aircraft which have not been delivered are parked at Boeing. That is tying up close to $12 billion in cash for Boeing. So of course, Boeing is using that as collateral to get all the debt financing they're doing, right? Getting all the bonds and raising money for that. The other thing is, because of that reason, on-time delivery, you'll hear me say OTD a few times, which stands for on-time delivery. On-time delivery metric rules in aerospace more than in any industry. Same reason, right? If you're late, a small part is late, and you're assembling a $100 million asset, you don't want that. It's got a lot of negative impact. So on-time delivery from supplier is most important. Of course, people will say quality is important, cost is important. Yes. In my 30-year career in aerospace, I've never seen a plant manager fired for quality, sometimes for quality, but never for cost. They always get fired for on-time delivery. So it's that much more important. Then the other thing is, in most cases, it's very high mix and low volume business, unlike automotive or other industries. So it's very difficult to think about doing optimization on the shop floor, just using your brain, right? Just talking. And so what we have found is you go to shops that are used to manufacturing a type of part with a very stable demand, and then suddenly the demand changes or the product mix changes, and all their assumptions about how they should schedule the parts in the shop go haywire. So it's very useful to have something like the tool we offer, which is called AdvisoryAero, and it can give you day by day, week by week, month by month, what is the best way to schedule your parts and what is the best way to size the batches. Another challenge is that in aerospace manufacturing, lead times are really long, especially if you're making parts that are made from castings and forging. They could be 12, 18 months long. And that causes a disconnect in short-term and long-term planning. And if you are not doing long-term planning, that comes back to bite you. And by the same token, because the lead times are so large, you are dealing with ratios of lead time to process step times, which are very, very large also. So that itself creates another problem, that when you're trying to do some simple calculations, or as you get more complex in calculating, doing optimization or simulation, your time steps, if you want to reflect the granularity of process steps, have to be very small, whereas the lead time is very large. So it becomes so much more computationally intensive to do those problems, right? Then it's highly regulated industry, so you can't do a lot of experimentation on the shop floor, right? In fact, for many operations, if you change a tool, if you change the setting of an equipment, if you change the ambient conditions, you have to recertify, requalify that process, and it takes forever. So you cannot do a lot of experimentation on the shop floor, and so the concept of digital twin becomes really useful. So we build using stochastic simulation, what is, equivalent to what people call digital twins, that people can do experiments on and on the computer without having to do it on the shop floor. And that really helps them improve their operations and, look at situation that they are thinking about conceptually, but you can see the results out of that as well. And finally, the demand is now volatile. Right now, we're going through COVID downturn. Things are starting to ramp up, but it's not a uniform ramp up. Military ramp up is different from commercial ramp up, and within commercial ramp up, wide body aircrafts are ramping up slower than the narrow body aircrafts. So how do you make sure that you're using your operations most efficiently in face of variable demand, and the rate of growth or rate of decline also being very different from product to product? So technology becomes important. Questions? All right, so that's pretty straightforward. Just pointing out why technology is important for aerospace manufacturing. So what are the pain points? So there are pain points within the factory, and there are pain points in the supply chain. Today's discussion is about factory only. It's not about supply chain so much. So let's just go over, one of the things we have done over the last 2 to 3 years is develop this suite of Industry 4.0 tools, which we call Affordable 4.0, because our target was these small manufacturers. So we wanted everything we do to be affordable for these small manufacturers. And in this technology suite, we have descriptive, predictive, and prescriptive tools to run your factory. And what they do is essentially is what's on the right side. So they will look at data, any data stream you have which is relevant to factory physics. It could be data coming from spreadsheets, access databases. It could be your MRP system, ERP system, PLM system for bill of material, any factory data if you've implemented IoT coming directly. And it converts it into a standard schema, which we call our standard digital factory model. So whatever data a client has, we convert it into a standard factory model, and then we apply analytics to it. So the analytics could be an optimization, it could be a simulation, it could be predictive delivery against demand, capacity analysis in the long run, whatever the client needs. All those different tools come into play, and then we give a very visual, easy to use user interface. So everybody from the shop floor to the CEO of the company has what they need and no more or no less. And it's something that they can understand and something they need to make their day-to-day decisions. So a shop floor person is probably not interested in looking at maybe even revenue projections for the quarter, but the CEO is. A shop floor person is more interested in seeing, if I have 2 people taking time off for the next 2 weeks because it's hunting season in Minnesota, how is that going to impact my delivery to the customer? What if I run 2 hours a day extra time, overtime, and run a shift on Saturday? Will that make the delivery commitment happen? So they can do all that stuff based on what problem they're trying to address. So that's fundamentally what we do. We basically hook into any data stream the client has, convert it into a standard digital factory model, and then we apply an analytics tool, and then we visualize it and give the information you need to make your decisions. So one example for a descriptive analytics is a tool we call AdvisoryAero. Every tool that we have is trademarked with an arrow in the end because it has to rhyme with the company name, which is AdvisoryAero. So AdvisoryAero basically gives you a full view of where your parts are. And it would seem to those who have not been on a manufacturing environment that, well, what's the big deal? I can tell you, even larger companies, if you go and ask somebody, where is my part number XYZ, sales order number this, when it's going to be delivered, it takes multiple phone calls and pushing of multiple buttons to come back with the answer. So imagine if you're the plant manager and somebody calls you from, you are a Collins supplier, and the Collins customer calls you and says, where is my part, which is due tomorrow? And then you have to make these phone calls and figure out what is happening and then respond. We make it in a web application. It's available at a fingertip for everyone in the shop floor. It not only tells you real time what's happening, it projects when the deliveries will happen based on past performance. So it uses some analytics there, some statistical analysis to show where the likely delivery date is based on past performance with 50% confidence, 90% confidence, and you can then decide what to communicate with your customer. In addition, it tells you, you see some flags here. The red flag tells you if a part has a quality problem with it. If there's a black flag, that tells you there's not enough purchase order in the supply chain. So you have to do something in the supply chain to make that delivery happen in the next 3 months or 4 months or whatever the case may be. So having this kind of a tool is pretty unusual in an aerospace shop. Even with the latest ERP systems where this kind of information can be mined much more easily, it's not real time, it's not as transparent, it's not as visual. So this tool has been, we're finding more and more people who are interested in this. We're just in the process of working with Boeing to make it as a recommended tool for Boeing suppliers. So that gives Boeing guys a visibility too for the part that are going to be delivered to Boeing. So it helps Boeing improve the visibility into the supply chain. Any questions? Okay, then let's go to another tool. We call it AdvisoryAero. SIOP stands for Sales, Inventory, and Operations Planning, which is one of the important processes in any manufacturing plant. You want to make sure that what you're selling, you are capable of making, and you have the capacity to make it. And if you have capacity open, then you better tell your sales guy to find something to fill that capacity in order to continue to run efficiently. And typically these SIOP meetings are, again, very anecdotal, and there are a lot of discussions with no real data in front of you. So we have built this tool which has an algorithm that does some scheduling, but primarily looks at where the bottlenecks are if you just went prioritized by due dates for the part, and you can start to see where you have a problem. So in the picture here on the left, blue is the demand for a certain part, and gray is the best you can do with the current capacity to deliver. So if you can see this 12 months in advance, there's something you can do about it, right? You can say, maybe I need to go to the customer and say this peak in the blue demand that needs to be flattened out. Or you can go to your operations team and say, do you need to add another piece of equipment or maybe hire 5 more people? But you can do it now instead of getting hit by it a year from now. So this tool works 12, 18 months in advance, depending upon the lead time of parts you have. And it has the ability to even respond to RFQs, because that's another challenge our clients have told us, that if a customer calls and says, I need 1 million pieces of this or 200 pieces of this, I just don't know what to commit when I can deliver that. So we have this tool that looks at blue, which is the existing demand, which is in the system, gray, which is the forecast by their sales team, and green, which might be a new RFQ or a proposal coming from a customer, and it'll tell you when you can deliver based on your capacity constraints. So the concept is simple. Applying this and doing it in a quick fashion, so it's not running overnight. That's the real challenge here.
So does it take data from the ERP system?
Yes. So all of these tools, when I showed this visual here, they will be implemented by converting every piece of data that you have, and bulk of it comes from your ERP system. But I have gone to clients who don't have an ERP system. They may have some version of old MRP system or some Excel sheets. So whatever you have, we just take it, convert into a standard factory model format, and then we can do any of these things to it.
So one more question for the predictive part. So it seems like in order to make this, you also need like a demand forecasting model.
Yeah.
So is that something that like your company comes up with, or?
No, so I think in aerospace, unlike consumer goods, there is much better ways to forecast because the long lead times actually forces people in Boeing and Airbus to give long-term forecast. If you actually look at Boeing website, they'll tell you what the expected deliveries are for the next 18 months.
Okay.
By program. So that's what we call, that's what is in gray is the forecast.
Okay.
Blue is where what's in the ERP system, which means Boeing has already sent you a purchase order. So it's already in the system. And green is if some chance order comes out from an air, let's say you're making a part which has a demand in the aftermarket spares world, and an airline calls you and says, we may need some of these parts. So you can put it in the tool and see what is the earliest you can deliver.
Okay.
Another, as I mentioned, to build a digital twin, we can do stochastic simulation. So I understand, I think Alex is teaching a class on simulation at this time. So some of the students listening to this may find it very familiar because we use Simio also. So using Simio, we can do discrete event simulation, using that technique, we can simulate a factory. We have done, to give you a benchmark, we can do a factory with 200, 250 people, 50 pieces of equipment, maybe 20, 30 process steps, maybe 100 different types of parts. We have done simulation in less than 2 months and give them results. So, in this case, we did the simulation of a factory in Tulsa, Oklahoma, where they were making flaps and slats for Boeing 737 wingtips. And we did the simulation. They were generally running some of these parts at a very large batch size because the setup times were long. So their initial inclination was, well, if the setup times are so long, we need to run larger batches for some of the machines, right? But when you look at the overall simulation and you look at every step and how things are outsourced and how things are deburred manually and inspected, we found that a batch size of 10 was much better, and that immediately reduced their lead time from 5-6 days to day and a half. And that helps you also free up cash because you have less inventory on the shop floor. Right? So simulation is very powerful, and so some people call it digital twin. Once we build a simulation, people can do whatever they want with it and study all kinds of what-if scenarios to address what they're trying to improve. Here's an example of simulation we did. This is the Tulsa, Oklahoma factory I was telling you about. In roughly, it was like 2 months project, and then within 6 months period, because there's an effectivity period, right? You can implement a solution, but you won't see the results until enough parts have gone through in the new system, right? So once we implemented this simulation driven improvements in the factory, we were able to get in 6 months time 30% reduction in inventory levels while maintaining fill rates and increasing the fill rates also. That's a lot of money, even for a small factory like that, where the value of inventory or stock on the shop floor was maybe $20 million. By releasing 30%, like $6 million a year additional cash available to them is a really big deal. Questions? So, I mean, just keep in mind that, it's not that you can just go and implement the tool. You have to do all the background work also. In that 2 to 3 months, you have to do the value stream mapping. You have to really understand how the parts flow. It takes a lot of time to collect, cleanse, and update data, because not everybody has good data. And most of the times, actually, it's bad data. Some data would be bad. That's something I can bet on, right? When you go somewhere, maybe process times are not good. Maybe there's not all the bill of material is not complete, whatever may be the case, right? So we spend a lot of time upfront cleansing the data. Value stream mapping is a good tool from, those of you who are familiar with the lean tools. It's just helpful to see a visual of what's going on in the factory at a very high level. And then you can build a simulation and then start to get the benefit from that. Okay, so let's go to the next tool, which is AdvisoryAero. And so here we optimize, again, the input is all those, data streams we talked about, bill of material, what is in the inventory in the stock, part routings, process times, setup times, what are the purchase part lead times, demand schedule. Dispatch just means what is the current state of the parts on the shop floor. And then you input it to this tool, which has a very good user interface. So you can pick what shift structure you have. You may have 2 shifts, 8 hours each. You may have 3 shifts. You may have 2 shifts during weekdays, 3 shifts during weekends. Whatever your shift structure is, you can input here. And then you can put the other things I was talking to you about, that people on vacation, a machine down for some reason. And you can put all that information. It will give you what the optimized schedule is and what the result is. So in this case, we were working with a factory where you can see going from roughly 40% on-time delivery to close to 100% on-time delivery only took 4 or 5 periods, which is roughly 1.5 times the lead time in that shop floor on that factory for that part. So very, very quickly, you can get to close to 100% theoretical delivery times. And there are other things you can plot, like how the overdues are going down, and it's all consistent. And you can also see how your equipment is being utilized. See, in this case, you see the top 2 equipments are almost 100% utilized, the rest are not. So if you want to increase the throughput, you probably need to do something about the first 2 processes, which are becoming bottlenecks, right? So in that optimizer solver, you have built in the digital twin of the factory. And now you're saying, how do I optimize that? And the optimizer algorithm does that for us. Just a little bit of technical detail here. I mean, you can read through this, but what I wanted to point out, we picked this multi-level capacitated large size problem tool or algorithm, theory for which has been there since, I would say, at least the early 90s. But it wasn't used very extensively, certainly not for problems like what we are using it for, simply because there wasn't enough computational power. But recently, 2 things have happened. On one hand, the MIP solvers have gone 1 million times faster than they used to be in the 90s. And computational power has gone up another 1 million times. So you have a net effect of 1 trillion times faster solutions. So that's one of the reasons we feel so excited about applying some of these advances in operations research, which are very robust, well-tried, very well-developed theory and mathematical construct, but they have not been used in practical sense because 20 years ago, you could not do this. Now you can do it on a laptop. You know, if you want to do it 20 years ago, it was probably an academic exercise on your, if you're at Cornell, Krishna, you know, using Theory Center, booking it for 2 weeks in advance for 2 days of running. So that's a big advance that allows us to use all these advances. And then example for that, we used it at a factory again. This is a factory that makes essentially control valves for defense and space. And 2 to 3 years ago, you may have noticed, you heard a lot more about Falcon launches by SpaceX. And they were just ramping up their launches, and they were building more and more of these rockets. And these guys were providing the valves that separates hydrogen from oxygen before combustion. So you need no leakage. You don't want any leakage whatsoever. And they are at a pressure differential of about 15,000 atmosphere. So they are almost like a sole supplier for SpaceX because of the technology involved in making those sophisticated valves. But they were making Falcon launches getting delayed. I mean, if you go back and look at the news, maybe 3 years ago, 4 years ago, they were getting delayed because of, they didn't say publicly because of valves, but our client was feeling the pain from Elon Musk's team on all the delays on Falcon. So they hired us to help them improve that delivery performance. They were typically at 40% on-time delivery at that time across the board. So they were supplying to Lockheed, Boeing, and SpaceX and Blue Origin and NASA. And again, we worked with them, you know, a few months time, I don't remember exactly, it was like 6 to 7 months time, we implemented the optimizer, we did all the capacity analysis, value stream mapping, and we doubled the on-time delivery by the time we left, and it was going up when we were leaving. It's a very powerful technique. I mean, it tells you theoretically how you can get to 100% on time, which means it's feasible. However, on a shop floor, there are all other kinds of variables that go wrong. So I don't expect that using the guidance from an optimizer, you'll get to 100% theoretical, but you can get very close because you're making the planning decisions, you're making the scheduling decision, lot sizing decisions, which are helping you improve. And if you have never done this before, and in this case, this supplier had never had SpaceX as a customer, and suddenly you have completely new product mix, which was dominating their complete product line. So it completely changed the mix on the shop floor and made all the tribal knowledge or the historical knowledge that people had on the floor or the planners had obsolete. So you either build that knowledge over time or you can run the tool and get it in a short time. So we were able to get 2x improvement on on-time delivery, and it was a very exciting project. Any other questions?
I have a question here, sort of more broadly. So how do these companies get these contracts? Is it through is there so especially in like these public project setting where like you see like this notion of winner's curse where the like if you underestimate your, like in this context, let's say, are you more likely to get the contract if you underestimate your like delivery time? Is that it, or is that the systemic reason for the cause of this not meeting on time delivery?
So there are multiple reasons, and what has happened in aerospace is, and this is my theory, so I'll stick to it, but you don't have to believe it. I used to be in engineering, so I used to be a chief engineer for a program at Pratt for aircraft engines. And I saw in engineering, people were using the latest methodologies, latest CAD/CAM tools, the latest in computational, both hardware and software, right? And as you went to operations and supply chain, you were living in the back, dark ages. And same thing happened to talent. all the smart people wanted to be in engineering, you had a lot of trouble hiring good, smart people, talented people in operations and supply chain. And so it was, and it's across the board. I work with Boeing, I work with Lockheed Martin, all companies, large and small, they put too much emphasis on, well, I shouldn't say too much. They put adequate emphasis on engineering and technology development. They put very little emphasis on operations and supply chain. Historically, it's changing, but historically, that's what they've done. So that's one reason. The reason certain suppliers have stayed once they've won a contract to supply is because barriers to entry are very high and it's a very sticky relationship because everything needs to be qualified and certified, and the whole process of getting a long-term agreement with a customer could take months. And now neither the customer nor you want to go through that again, at least not for the next 2-3 years if the agreement was for 3-5 years, right? So it's the nature of the business, so one of the outcomes of that is, which is very interesting, is that while there's something called profit pool analysis, which was done recently by one of the consultants, if you look at the profitability by company or by tier, OEMs are making roughly 5 to 10% profit margin. Guess how much tier 1, 2, and 3 are making? They're making 20, 25% margins. Because once they got the contract, they're set and they're going to optimize their process to cost, not to delivery. And they know that a customer has to put in so much effort to change with a supplier.
Okay.
So it's a very sticky relationship with suppliers because of the nature of the business. And there's a complete lack of transparency. When we work with Lockheed Martin and go into their supply base to help them improve either the cost or the delivery performance, we know the both sides, how suppliers are, how customers are. But you can see there's a disconnect between how suppliers see customers and customers see suppliers. It's a very, it's not like automotive where things are so much transparent. You can pretty much say, if you are Visteon supplying to General Motors, your profit margin must be this. In aerospace, it's so opaque. I have come across simple machine shops making 25% margin. There's no apparent reason. There's no differentiated technology. There's nothing that is, a recipe which is secret. No secret sauce, but they can because it's just lack of transparency. So one of the things, that's the reason why Boeing likes this tool, that even though it doesn't go into the cost, but at least it tells you a real-time movement of your part at a supplier. And by the way, suppliers should have no objection sharing this information because this has no cost information. It doesn't even have process times. So it's not sharing anything other than what Boeing needs to know anyway.
Okay.
Right? It's a long answer to your question, but...
So maybe as a follow-up then, so do you see a lot of vertical integration that happens? Because it seems like if there's a relationship is anyway sticky, would you want to pull that into a business?
Yeah, so customer can think about vertical integration strategy, but the more integrated you get, it's actually very bad in the downturns, right? Because your overhead structure goes out of control. So you only want to vertically integrate, if you're smart about it, is when you want to acquire some technology that you don't have, or if these are parts which are so critical that you have only one source, and you want to control that capacity, so that supplier is not playing Airbus against you if you are Boeing. Right, so there are other business and technological reasons why you want to vertically integrate, but just in general, these small shops, they usually don't have a secret sauce.
Okay.
Some of them become very good at producing because they have done it for a long time. Or they may have adopted their tools or equipments to do certain things that comes by doing something over a period of time. So there's a learning curve for sure. And if you bring in a new supplier, it'll take it that much longer again to get to that learning curve.
Okay, thank you.
Yeah. Okay, and then finally, what we as a consulting firm are thinking and what we are seeing in aerospace manufacturing is that especially for small and medium-sized suppliers who are very cost sensitive. They want to see that the implementation lead times and costs go down. And that is the reason why ERP system companies like SAP, they are not getting the penetration they were expecting in that tier 2s, 3s, and 4s of aerospace. So now you have, as a result, you have all these smaller companies that have come up like Infor and Epicor. Two of them are actually in Minneapolis, that make their own ERP system, which are kind of like SAP Lite, SAP Lite, or even lighter. But even then, it takes a year plus of implementation, up to $1 million in investment to implement it. So we know that's the pain point. So what we're saying is, hey, you don't necessarily need this latest ERP system, which has all these bells and whistles. What you really need to do is use your data stream to make your shop more operational, and we can give it to you by this simple tool that we have developed. And that can be implemented in a few weeks' time at a fraction of the cost. Of course, it doesn't do everything that ERP system would do, but it does actually in some cases more than what an ERP system would do. So it's a choice that our clients are making, whether they go for an ERP upgrade or a new ERP system, or they look at these targeted technology solutions. So that's one thing. The second is, one of the reasons technology implementation takes a long time is because the early part of data cleansing, formatting, collection is very laborious. And so, we are very interested in looking at methods, automated methods to do data diagnostics before you even apply that data to your tools. And this is a fact of life in any application in data analytics, right? It's not unique to aerospace manufacturing. If you're doing sales, if you're doing any optimization in a healthcare industry, wherever, what have you, getting good data, accurate data, and complete data is important. And so that's one thing we want to work on potentially in the next few months. And then, as I mentioned, some of these computations are taking a long time. You want everything to be done. Our magic rule is that everything should be in less than 5 minutes on a laptop. If it takes 15 minutes or an hour, it's just something people won't use very frequently. It has to be less than 5 minutes. It has to be on a laptop. So that's our attempt to bring all our simulation and optimization and descriptive tools to that level. And we are there for most of them, except for some optimizer problems, where you have a whole bunch of parts, whole bunch of process steps, etc. And then, Boeing has a big initiative called model-based systems engineering. Various versions of that are being used at other places. I know Pratt & Whitney has, Collins has, which is not just designing based on IT system, but having a whole life cycle of the product, including building, supplying, and aftermarket support, all done on a computer. So all connected in a one big model that accounts for the entire life cycle. So the kind of work we are doing can naturally plug into that, because we're going to bring in the operations piece of this and a very inexpensive, quick way to do that. And it can be connected with the CAD/CAM systems. It could be connected downstream with whatever aftermarket system they may have to build the entire life cycle model. And then there are some other things like applications of Internet of Things for connected factories, lights out machining. You don't have to be present when the machine is running. And closed loop manufacturing, which basically means you're doing quality checks as you're manufacturing. All these things can be done using simple analytics methods. And finally, automation is more than software, but it's something where digital technologies can help as well. So I think I am on time or before time, 3 minutes before time. Welcome any questions.
Thank you very much for this wonderful talk. Thank you. Yeah, so we have quite a bit of time for questions. So
I have two questions regarding the AdvisoryAero software. So I wonder if the solver used in the software is some commercial solver available in the market, or it's some solver specially designed for this type of problems?
So our attempt is always to use what is available instead of reinventing the wheel. People have spent years and decades in developing, efficient solvers. So we have, in the optimization world, we have used Gurobi and Cplex in the past, but one of the challenges there is that they have hefty license fee associated with that. So if you're going to, you can imagine going to a small shop and saying, okay, here's a optimization solution. And they say, okay, I'm going to pay you, and then I'm going to pay Gurobi on top of this. That doesn't make sense, right? And it's not a small amount. Gurobi and Ample together could be 15K to 20K a year of licensing, right? So what we have done is we are offering that solution in our tool, but we also have open source solutions where we have used Python and CBC open source solver.
Oh, I see. And then I have a second question is, so as you mentioned, there's like a feature of high mix and low value of those parts from the suppliers. So I wonder how this actually affects the optimization model you use, because you mentioned like this optimizer mainly depending on the advanced development of mixed integer programming solver. But I'm thinking maybe because of the future of high mix and low value, the mixed integer programming model will be of very large size, which can pose lots of computational difficulty. So then is there some like technique you can kind of employ to validate?
I think that's a very good question. So, we always are looking for ways to speed up our solver. And what we have found is you can go from one shop to the other, and one shop may have very high variety or high mix, and the other may not. And when you have high variety, that means suddenly your matrix became huge, right? So we were working with a fastener supplier, and they had 30,000 SKUs, part numbers, right? And so with that many part numbers, each one with their own bill of material, going through their own process steps, makes the problem huge. So we try to simplify that by trying to define working the solver not at the part level, but at a part family level, where part family is defined as a group of parts that go through the same process steps and have roughly comparable process times. So then you can say that's a part family. So then I can put all those parts under that part family. And instead of running for 30,000 parts, I could probably run them through, 300 part families. So that's one way we have used. But if you know of other methods, we'll definitely be interested in talking to you.
Yeah, thanks. Yeah, and very interesting talk.
Okay, thank you. Any other questions?
One thing I'm curious about is in terms of like simulation validation. So one of the things you mentioned is what do you call virtual twin? You build a very realistic simulation of the factory. But I was curious if you could talk about validating that simulation and making sure like what you get out of the simulation matches up with what you actually see.
Yeah, I mean, just like with any tool, I mean, we have standard DevOps process that has pretty important piece of that is validation. Once you think you have solved the problem, you have to validate it. And how do you validate it? So for different types of problems, different types of data availability, you have to do some high-level sanity checks. You have to look at the past history and apply as if you are predicting what has already happened, right? So you can validate things that way. So one of the things we do for optimization, for example, is once it's done, before we do any future predictions, we run the optimizer for the past performance of the shop and see if the optimizer does any better. And if it does any better, what does that mean in terms of scheduling and batch sizing? Now, if you don't have too many part numbers, batch sizing becomes very important. So you can start to see if batch sizing alone could explain the discrepancy between what happened versus what could have happened with the optimizer. So you try to apply sanity checks, but unlike a physical system where you can do experiments and check everything, there's only so much you can do with data. And as long as you pass all those sanity checks, which are pretty rigorous, looking at the past performance, looking at some KPIs or KPOs, let's call them. So let's say one of the things which really stands out very quickly is how your resources were utilized in the past, because you have real data for that independently, and you have it from your theoretical calculation. So you can start comparing those things. You can also start to look at some other key process outputs like lead time for different parts, and do the ratios of lead times of those parts make sense? Do individually they fall in the distribution of the past performance? So you try to find smart ways to validate, because in the absence of actually doing an experiment to compare, that's about the best you can do.
Do you ever go back and once you come up with these solutions, right, and you say, if you do this, maybe your on-time delivery will go up to this number, right? Do you ever go back and compare like your projected improvements to what they actually saw? And if so, could you talk about how well they tend to line up?
Yeah, so that is, we do it because we want to see how the tool is holding up, and many times these tools are under some kind of licensing agreement, so it's not like we leave the tool and that's it. We have an ongoing relationship with the client, and there's a maintenance and support that goes with it. So we know if there's something not going right. What you find is, as I was saying earlier, it is near impossible to get theoretical maximum results, right? So when I say that optimizer with this kind of batch sizing and this kind of scheduling can give you, or this kind of resource allocation can give you up to 100% on-time delivery, we know that it's not going to be 100%, because there are so many other variables on the shop floor. People getting sick, parts getting scratched, quality problems occurring, that you really won't see the exact comparison, but you see the direction. That's why I gave you examples where there were dramatic changes, right? Going 40% to 80% on-time delivery, right? For 6 months before we got there, everything was hovering around 40%. After we left with the tool, it started to go up and kind of started hovering about 80%. And if you look at the inventory reduction, it went 30% improvement in 6 months. Again, it's not something, you can almost see the inflection point in the free cash flow graph that their CFO showed me. So it's, those kind of things are very easy to see. And I do think, I worry if you are looking for some small incremental changes, how much confidence you can have in saying that it was because of the tool and not because of something else happening. So that's where I think I often see presentations in industry where a technology consultant or a company would come and say, we improved cost by 2.5%, or improved delivery by 3.25%. And I said, that's all false precision. It's all in background. Just given the uncertainty and the fact that you're not capturing everything in factory physics that is really happening, we can probably estimate that if you are rigorous about it, as to what that band is that beyond which, if you see improvement, that could be attributed to the tool. But it's certainly, 2 to 3% type numbers that I see in industry and publication sometimes. They don't impress me. Does that answer your question?
Yeah, that does. Thank you.
Yeah, sure.
Okay, so I mean, we can end the official part of the talk here, but we have like about a 15-minute reception. So if anybody who wants to stay and ask questions are welcome to, but others, if you want to leave, you can.